Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk.
Hey, Fred.
Sorry about the mix-up on the schedule this morning. I was like back and forth, and I had inadvertently thought I double booked myself, but one of them was for next week, and I was like, so we bounced around a little bit. But anyway, good to talk to you. It's been a little while.
It has been.
Yeah, and so I thought, well, I was reading an article this week that made me go, I got to talk to Kirk on this because I know he's guilty of this all the time. And it's this concept. It was all about, the article series was on how people make decisions. And the one that caught my eye was the confirmation bias. And I thought, I'm guilty of this because there's so much information in the world, and you're sorting and filtering and looking at this and that signal and piece of information. You go, well, I like that piece of information. I'm going to put that in my report.
Yeah.
And I've run into that with HALT, where I'm sitting next to a client and we're, trying to break their product, and something happens. They go, oh yeah, that happens all the time. Yeah. And they choose to ignore it. And then I almost always probe, well, why did the screen go dark? And in this particular case, we were going really cold. And it was an LED screen, and the technology itself does that when it gets cold. And if you warm it back up, it's just fine. So, there's a rational reason for that. That makes sense. Right. And then other things, in other circumstances, we see something. But one of the things, and I know you and I have talked about it before, is when you're trying to get an organization to say, oh, I understand HALT, this is why it's useful, is we'll take an existing product that they know how it fails. It's maybe in the field already, or they already know some failure mechanism. Right. And you run a HALT on it, and you say, look, 8 of the 10 things we found were things you already knew about. We could have found them and solved them much, much earlier. It's kind of the argument, right? Yes. But that's not confirmation bias. That's using we already know this stuff, but we could do it quicker kind of argument. Whereas, but sometimes you've run into it where somebody says, oh, that problem, and they jump to the conclusion of what the root cause is, but they haven't really, they see a symptom. And I'm like, how do you know that that's what the cause is? And you see it more, I see it more in root cause analysis. But you see it right at the side of the HALT. You see a symptom and somebody goes, oh, that's just this.
Yeah, I wish I could tell you some recent information, but, the NDAs keep me from doing that. Yeah. But I've definitely seen that quite significantly, and not understanding that HALT is a margin test. It's not, pass or fail. And, the things that occurred in the field that were because of a low margin. Oh yeah, we knew about those, those have been a problem. I said, okay, we took it very cold, and you saw that there wasn't much margin. As soon as it got past barely, a very cold room where the air conditioning was turned down to
so like
55.
So something like 1020, 10C or 15C.
Yeah, you see, you're already having problems with this particular mechanical system here. And I said, oh, yeah, we knew about that. I mean, that was a field. I was hoping we'd break it. And I'm going, well,
if it's not working, it's a break.
I mean, you found a limit. Okay. Yeah, you warm it up. You didn't break it. I mean, you didn't cause it to catastrophically fail so that when you remove the stress, it comes back to a normal condition. Mm-hmm. Yes, that's true. But you see that your margin and your correlation that you've already had out in the field with the many units you have has shown that is a particular weakness, and there's quite looking at your Pareto chart,
it's causing
you probably
you problems,
see
yeah.
if you have a Pareto chart.
Yeah.
First of all, you've got to document your rate of your number of incidences of this particular mechanism or these limitations. And if that was what here I am trying to motivate them to start using stresses beyond any use condition ever that they'll ever see.
And you're in the realm of a good air conditioner.
Yeah, and this is probably a product's going to use all over the place, all different places of the world, and maybe they don't have the greatest anyway. But they do see that they saw the phenomena at room temperature, certain conditions, and I said, well, your variability between this particular component that is disposable and the variability in its required, physical characteristics are probably enough, and you don't know what it is. You haven't tested thousands of these disposable parts, and that's gonna. But the manufacturer is going to have variation, and the required particular dimension that you're talking about. This has already been a problem in the field. You've seen that. Now, yeah, but they're always expecting something dramatic to happen in HALT, like something catch fire. I don't know what they're expecting. But
I've had that happen a couple of times. It is exciting. It's not very often, though.
No, it's not very often. It's very infrequent. And in fact, as I've talked about in the HALT of digital electronics, or which are most systems, computers, almost always you're going to get an operational limit before you have it blow up.
Yeah.
The only place where that's most likely to occur is in power supplies, because
there's a lot of energy there.
There's a lot of energy, and many times the operating limit is at the same point the destruct limit. Yeah.
There was one, and I think I've told you about this one before. Is I was working with a team, and you were using an optical drive. To run their system, and so it's like a CD, looks like a CD, kind of looking thing, and you had to have it for the system to work. It was the way they controlled the process, or the cost of the system, the subscription of the system, whatever.
Right.
And they were getting a whole raft of these things that came in with scratches on it, and once they were scratched, it couldn't be read anymore; it would fail.
Yeah. Okay.
And it's so they had a lot of information, and the first thing they did is well, what optical drive is this occurring from? And they were looking for, is it a particular batch? Is it a particular group time that we're making these, whatever? And so the span that they were making them in, it was like one vendor of optical drives was predominant in the make at that moment. Mm-hmm. And those got to the field, and they were getting the scratches and stuff. And so they spent weeks and weeks tearing apart optical drives to find what was scratching these things, and calculating clearances. And they were just hounding this vendor because they were already convinced that it was the vendor's fault.
Okay.
Right. And I looked, and I was just curious because this poor guy, this technician that was, in the same room as I'm in, he's tearing these things apart and looking and not finding anything. There's no smoking gun in these things.
Okay.
They had plenty of clearance, even when they got really hot and they got all this other stuff. And I said, well, what do the scratches look like? And they were like on the North Pole and South Pole. And sometimes they'd be on like the east side, and they'd be little short scratches. They'd be not more than a half-inch long.
Okay.
And they'd be like 2 or 3 of them on each pole. And well, that's odd, because if it was a clearance thing, you would think that scratch go all the way around, or most of the way around.
It'd be circular.
It'd be circular and go all the way around, and they weren't.
Okay.
And I said, what happens if you heat up just the optical drive or optical disc, the disc, and it immediately went into a potato chip structure.
Right. And so it started scratching because it was warped.
It was warped. Yeah. And they were convinced for weeks that it was the drive maker themselves.
How did it get heated up?
Well, this is an example of an amazingly bad design decision, because the optical drive had a port in it, right? It had an opening to the outside.
Yeah.
They exhausted all of the CPU and GPU and all the other crap that was inside this thing, running at extremely hot, forcing it to its limits.
Yeah.
Was vented out through the optical drive.
Yeah.
And so the optical drive was at, I think we measured it at like 100 C. You could put a cup of tea next to it and it would boil. It was so hot.
Wow. That is amazing.
And it's like, didn't anybody look at the scratch marks? Somebody had some data, and they were, and then they had other legitimate vendor problems. But
it wouldn't unwarp when it cooled down.
It would. It would definitely it would go flat again.
Wow.
Yeah. No, it wasn't. It was enough to, it heats up and it expands, and the expansion's got to go somewhere. So it made a potato chip, but then it cools down slowly, so it just settled back out.
Wow, that's bizarre. Anyway, but
that's an example of confirmation bias. Is you have tons of data, and I know you and I have both experienced this. Is where you have what's this failure mechanism? What's happening here? What's causing this?
Generally, of course, you want to look outside and you want to blame the other, the vendor, supplier.
That's a different bias.
Well, that's a different bias, but we couldn't do anything wrong.
There's that too. There's the whole problem. That's another topic. But there's, when you're going into HALT and you're seeing a symptom, or you're looking at a field problem and you see some symptoms, and we go through the due diligence of saying, was this limited to 1 week of production, or is it from one vendor, or is it from one time slot, or is it one part of the country that's having this? Or we try to isolate, is this a big deal with every product we shipped, or is it limited? Is kind of the triage right at the start. And usually we're looking at all kinds of information. And so, let's blame this vendor. It looks like it's their fault, is convenient because we get lots of vendor problems in the past, and it must be that, and we really hope it is that, and then it's not our fault. But that's a symptom of confirmation bias, and somebody made that decision and went with it without really understanding what was the root cause, or what was the underlying issues,
or what was the probability of something happening, as far as a unique kind of condition. Mm-hmm. For instance, I've had clients that had a rash of failures of one particular sub-circuit, like a microcontroller for a motor, okay? Yeah. And, they said, we've had maybe, 15 to 20 fail out of, 300 units. Okay. And I'm going, it's probably just, would we do better if we bought military grade components? And I'm going, no.
It just got out of your profit margin.
Yeah, exactly. And I said, it's just infant mortality. And if we, bought better, no, you don't even know what the problem is, because you haven't gone in and evaluated the circuit and looked at, the feedback of the external signals going into that circuit board to see if there's a fast transient or there's something that's very difficult to see, but it's pounding on that particular microcontroller's inputs more than it would ever expected, and you won't know that, but you're killing them, and you're not so the first thing to do is go in and start analyzing that particular interface. Where
what's the source of the energy that's causing the problem?
It's probably back reverse EMF from a motor.
Yeah. Well, it's one of those things where a client years and years ago says, one of the ways I look at root cause analysis is the component that failed. Was it the source of the problem and it killed itself, or was it a victim that something else wasn't going right and killed it? Or was it the hero, that it's like a fuse, it sacrificed itself so nothing else would get damaged.
Yeah. It saved the other, fuses. Anyway, it's a real problem, because it's so easy to say, it's infant mortality.
It's ESD. That's one of my favorites.
Something like, whatever they say, they don't know. They've got a blown up chip or whatever, and they're not looking, to investigate further. They don't have the resources, whatever they're complaining about, or they don't have the technical expertise to look at. I said you have to get a sampling scope. You may have to get a very high speed scope to see the transients coming back from that circuit, because even if you have a shunting diode, a shorting diode,
still gets through,
it's still got a pulse. It's still got a resistance and probably a
a bit of current coming at it. Yeah.
Yeah, exactly. A back anyway.
Well, capacitors what's it called? Not chatter.
Yeah, you might be able to put a capacitor though in that
to
circuit,
dampen it. Yeah.
To dampen it or to short it to the ground, and it probably would be a nickel charge. And I didn't see a capacitor doing that in that circuit in the schematic. So I'm going like, okay, and that was just like one of the many problems that we were going through. So we didn't dwell on that, but I had told them several times that it needed more investigation before you determine it was infant mortality. And
well, one of the things with your experience, and this is kind of where it becomes a gray area in confirmation bias, in my opinion, is that if you've got a lot of experience and that you look at a circuit board and it's got two electrolytic capacitors, so the CAN capacitors with two leads sticking out on the board. And for whatever reason, they give it like a 1/2-inch clearance from the board to the base of the CAN. I would look at that going, I'm going to make a major presumption here that those capacitors leads are going to break in the vibration part of our test here.
Right.
And like, no, we've never seen that. And, 5 minutes later they break. Mm-hmm. Whereas some things you and I could just look at it and go, that's going to be a problem. In other times it's we're not really sure. Let's go find out.
Right.
We're not perfect either though. I'll say, it's like screws backed out on a field failure and it shorted out stuff. And they were ready to take the CPU and send it back to the vendor to say, why did your CPU short out? And there's a screw welded to the leads.
Yeah.
Come on. You have to pay attention to the evidence you got in front of you.
Right. But some of it also keeps you from, they say, oh, yeah, we knew it'd break at 60 degrees C. And I'm going like, no, you didn't. And no, why did you say that? Your
data sheet says it'll go to 100 C. So give me a break here.
Right. Or
it's rated for 80 C. Why do you think it's going to break at 60?
Right. Or something like that. It's 125 C. And besides that, usually it doesn't. So in fact, that helps clear up their confirmation bias if they've never tested beyond spec.
Yeah.
But the real test when you go to find something in low margins is getting the engineers to improve that margin if there is no field, failure data coming back.
Well, the example of confirmation is that bias from the engineer's point of view of this is like, well, it didn't break. We heat it back up, it works. It's in spec, it still works. The design is good. And it's, but all right, now you move, to 65 Fahrenheit and it breaks or it slows down or it malfunctions in some way or another.
Right.
I find that the getting it to work is a real challenge for any brand new design, is just get the first ones to work. It's very rare that somebody builds something
and it works
first time and it works out of the box, out of the prototype.
Sure. Right. They get it working on the bench and they're
really
you get
it working and then ship it. And it's like, part of the engineering has to deal with variability. Well, the customer would never do that.
Exactly.
It's like
the biggest myth in the business. Well, it'll never see that in its in-use environment. Well, the customer will never. Yes, you're right, but you don't recall cumulative fatigue damage. Cumulative, okay? We don't have time to accumulate all the fatigue damage it's going to see over 5 years. So
give it margin.
We'll give it margin and err on the side of more margin than less if it doesn't cost too much.
Yeah.
That has to be a factor. Yeah. And we're not going to use special materials or change the water cooling from air cooling. We're going to do what we can with the reference design and removing the weak links. And it's amazing how far you can go with that. Yeah. Just standard technologies. You talked about the LCDs. Yeah,
it was LCD screen. That was what
LCDs,
it was, that blanked out cold.
The chemistry of liquid crystals doesn't allow it to
it wasn't much below zero. It was about
right. And I've had that I did laptops at Dell and all that, and I had to have the screen on there, and it would go blank.
Yeah.
But I'd still have it processing and running, and I have external monitors that I could see the product running fine.
Yeah.
I just couldn't see anything on the screen, but it didn't damage the screen.
Nope.
And when I went, the same thing, when I went hot, usually it didn't damage the screen either, because, it quit operating in the fact that it couldn't display anything, but it wasn't destructive to the screen. And so, that limitation is something we can't really overcome or shouldn't have to worry about it, because
but now we don't use LCD screens anymore. So, we have other materials that give us a bigger range and more, now you can sit on the top of the mountain at minus 40 degrees and it'll work.
Right. You're right. They do have that, and they're improving on, the building margins and more capabilities in whatever they build. And certainly that's important.
Well, we've talked about it, a handful of ways that confirmation bias and, paying attention to the data that is related, jumping to conclusions is probably the way I'd mostly often see it, is one example of it. And that might not be totally accurate. There's a bunch of other problems with how we make decisions. But the idea is that the first step is to be aware of it and guard yourself against that. What is the evidence? What is the actual, physics, chemistry, whatever it is before you make a decision, did you consider appropriate range of information in order to make a good decision? Yeah. And it's hard because spotting the thing you think it is and jumping to it really gives you this sense that you saved a whole bunch of time. And unfortunately, sometimes based on your experience, you're right. Yet that experience can also lead you really far astray. And so it's just be cautious. It's one of those things, be aware that we do that. It's natural. It's built into us in our DNA, and just be aware of it and double check yourself, before you dive off into a decision.
Right. And I think that sometimes our confirmation bias in our case, and sometimes with a consultant, knows that their confirmation bias is, of course it's not going to work at that temperature because it was not designed to do that, turns around to saying, no, we can go higher temperature, because I have known from my many years of experience that most solid state electronics can run at much higher temperatures. So we're going to keep increasing it. So, that it works both ways. And our experience does help us kind of cut through some of the challenges that we have because of the confirmation of, above spec is always going to cause
it's always bad. It'll fail immediately.
Right.
Yeah.
So
no, and you really do want your system to operate well above spec.
Exactly.
That's
you've got to have margin, because design engineers really don't have and we don't ever really know the total distribution of the stresses in the environment
and the combinations
and the variation in the components and margin capability of each individual product you build. So
anyway, it was one of the handful of articles I read this week that were on decision making, and this one I thought, Kirk and I got to get into this one. We know about a lot about this one.
Yes, we've confronted it many times.
Yeah. Anyway, so if you're listening to this and you go, well, Kirk and Fred, they know a lot of stuff, so they hopefully we just confirmed your bias of that opinion. So, so if you've got a bias or an idea or a thought on this one or other topics, we'd love to hear from you. It's been a little dry, Kirk, lately for getting comments and stuff.
Oh, no.
So we got to hit the button a little more harder, I guess. If you're still listening, here's your challenge. Go, think about what you're working on or what's the challenge or something you're curious about, and head over to accendoreliability.com/go/SOR and let us know. Or Kirk and I and the other hosts are available through LinkedIn, or on our About pages, we have our contact information. So plenty of ways for you to get in touch, and we look forward to hearing from you and what's on your mind and what's challenging or useful or whatever. We'd love to hear from you, and then we'll get you an answer or our thoughts, and then most likely we'll put it into a future show. That's kind of why we always ask.
Yeah. We love hearing your comments and feedback, positive, negative, everything. So let us know.
Yeah. And unlike YouTube, you don't have to hit the like button. So, or whatever, subscribe button, whatever. Hey, thanks, Kirk.
Yeah, Fred, we'll talk to you soon. Okay.
Yeah, take care. Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.